Okay, hi students. Welcome to ENS 3105 or 6132, depending if you're undergrad or master, mechanical design and development. Okay, so this is lecture number 1, where I'll give you a bit of an introduction to the unit. First of all, I'll give you a bit of background on myself. Okay, so I'm obviously a mechanical engineer, and I studied mechanical engineering because I thoroughly enjoy mechanical design. Really, it's the reason why I studied mechanical engineering, purely from a design point of view. And so obviously I've had a lot of design experience over the years, but for me it really all started with, I guess, Lego as a really young kid, where you have a very early form of creative design and some basic forms of manufacture. Okay, and so you have these well-defined building blocks as such, and you can then put these together and assemble them in, I guess, an infinite number of possibilities, and you've got infinite forms of creativity. So that's where a lot of early design and design for manufacture started for me. My dad has a manufacturing business, so then I was exposed to a lot of real world manufacture. And then following that, went through and did a lot of machine design, design for manufacture. And then when I was doing my undergraduate degree as a mechanical engineer, designed numerous race car components and suspension components, and even went through and designed for my honours thesis a hydraulically interconnected suspension system for a race car. Then while I was doing my PhD, went through and was working as well for a mining company looking at gearbox and drilling equipment designed for exploration drilling. And then since then, I've done lots of design work for research test equipment, etc. So that's a bit of a background about me and a bit of my history in mechanical design. I hope that you enjoy mechanical design itself, and I'm sure you will, because it's a very different unit to what you've probably previously studied, where previously you've looked at in your units, putting numbers into equations, but this applies a bit more creativity to mechanical design, a bit of creativity to the theoretical work that you normally do, which is very interesting for students. They find it quite rewarding. Okay, so a little bit on my expectations. So I have pretty high expectations of students. I want students to think and to push themselves. So I always put a little bit of pressure on students to find out what their capabilities are. So you'll get a lot out of the unit if you invest into it. Okay. As a marker, I find that I'm reasonably generous. As long as you've got something there and you're making an effort, I will give lots of part marks, etc. Okay. Okay, now just generally, UTI feedback. Thanks a lot for the UTI feedback. In the past, obviously, you haven't feedback for this unit yet, but previous students have. And I use a lot of this myself to obviously improve the unit and continually aim to address any issues that students have to make this and any of my other units the best units the university has to offer, so students get a lot out of it. So based on some previous UTI feedback, some comments that I have made, so listen to the student's voice. I've included a lot more worked examples in the tutorials. For instance, I will be applying this year more past exam questions, so I haven't normally used them before, so you can see exactly what sort of expectations there are for an exam style question. Previously, there has been a week delay in the lecture example solutions and tutorial solutions. I've removed that now. So all the lecture material, apart from the recordings, I'm doing them now. And I'll be doing them throughout the semester, so there'll be weekly updates for those. But the lecture slides and the tutorials and the tutorial solutions and the lecture solutions are already uploaded for every week for the semester. So you can go through ahead and start reading them if you want before any classes. So that's something which I've changed, which the students like. Now, tutorials. So I prefer very conversational tutorials. And this was very difficult in 2020 with the COVID situation where a lot of it was online. However, now we've returned back to class. Okay, the tutorials will return to how they were before. So students will really enjoy that. And I do stress that although the lectures are obviously good to attend, I find students get a lot more out of the tutorials where they're all applied lecture material, working through examples. So with that, you know, it's very conversational. And so rather than me just sitting up there talking, we'll work through a problem together, okay, and see if we can find out where you're actually struggling. Now, I don't provide solutions to assessments after they've been released. However, if you do have any concerns about your marks and whatnot, please feel free to approach me and we can go through and discuss any of your queries, or I can go through how things would normally be worked out if there's any issues there. Okay, so I won't give the solutions, but I'm happy to discuss them with you. Now, recorded lectures. Okay, I don't think I'm going to do these in class because in class I'd like to be a little bit more conversational, and I don't think it's going to record the best. So what I'm going to do is do pre or post recordings for the lectures. So we'll run a lecture in class and then I'll do the little bit of extra work and I'll pre-record a lecture and upload it, or depending on how the week is, I might do it after the lecture. Okay, and then we upload it to Blackboard. There's real-world applications in the project. Okay, with the project itself, it's a real-world application. So I like to make this as applied as I can. So you can't get much more real life than mechanical design, advanced mechanical design. These are probably the most applied engineering units that you go studying, and you'll start to see how all the other units you've been studying in your course sort of come together. And that's why these two units are sort of considered capstone units to the course. Okay, so in mechanical design and development, so we'll be looking at more smaller static design projects. In advanced mechanical design, we're looking at complex dynamic real life projects. So this is more of an introductory unit, and then advanced mechanical design is where we step up to real world applications. Okay, and like I said before, I do provide follow-through marks always. Okay, however, if you feel there isn't, please feel free to see me. I'm very approachable and happy to discuss it. Okay, early in the semester I can be quite busy as course coordinator with lots of student appointments. So if you just send me an email, we can make an appointment to see me. Okay, so starting off with the unit. So engineering design is commonly recognized through its products, and products success really indicates if we have a good or bad engineering design. So here I give you some products, okay? Generally in class, I'll do this conversationally, but I'm just going to talk through this one. The top car you can see there in the Golf colors is the Ford GT40. So it's a British American 4-time winner of the 24-hour Le Mans, so from 1966 to 1969. Okay, and it was Ford's first and only American constructor to win Le Mans. So as a designer, when you're sitting down trying to design this car, you'd probably have one objective in mind. Okay, it's a race car, and so you'd have one objective in mind, and that is to win races. Okay, it doesn't matter, you know, some may say, oh, you want aerodynamic, you want it to be slick, or you want the big motor and stuff, you might want big tires, so it's lots of grip and stuff. These are all secondary objectives to the main objective, and the main one is to win races. And so is it a successful product is if it actually met that main objective, and it did. Okay, it won 4 times in 24-hour Le Mans, so you would say that this is a successful product. The one below that, you may recognize it from Back to the Future. Okay, it's a DeLorean DMC-12. Lots of creativity on this car. It's got gull-wing doors. It's got a fiberglass under. It's got non-structural brushed stainless steel bodywork. It had some new untested manufacturing techniques. So it's things like elastic reservoir molding, which was presumably to help the car be much lighter and lower production costs. And so all this new technology that DeLorean worked on and generated all these patents, turns out that they were actually unsuitable and didn't really work. So the car actually didn't make it to production successfully and didn't really make that many sales. So they ended up making this movie, Back to the Future, to try and revive the car. This was following Colin Chapman from the founder and owner of Lotus, who came through and replaced a lot of the unproven technology that DeLorean were trying with proven technology from Lotus. And the car was completely re-engineered, then made into a car which you could actually produce. And then they made the movie Back to the Future, but it was a little too late, okay? And the car had very bad marketing previously, and so it was hard to revive it. Okay, so that's an example of a good product and a bad product. And the GT40 actually was that good a product that they redid another one, okay, more recently, which you would have seen. Okay, here we can see that there's actually two sets of brakes. Okay, on the left we have Brembo brakes. Okay, so these ones here you can see they've got 6 pistons. There's 3 on this side and there'll be 3 on the other side. It's got deglazing grooves on there. It's vented disc. Okay, on the right we have an AP Racing brake setup. So once again, this one's got 4 pistons. There's 2 on this side, 2 on the other side. It's got cross-drilled discs with deglazing grooves. And so we ask ourselves which one are the better products. And you've probably seen the one on the left more, okay, the Brembo brakes. And that's because the Brembo brakes are generally used for production cars. Okay, the AP Racing one, it sort of says in its name, this is for racing applications. And to be honest, both of these products are actually very, very successful. Okay, they both apply very good braking systems to vehicles. Okay, but what's different here is their application. One's for production cars, one's for racing vehicles. This one here generally sparks a bit of controversy in the class. Which one's a better product, the Mac or the PC? So this one here, the Mac, is really a computer for, I'll sort of say, non-computer users. Okay, it's sort of a little bit lower on the functionality. Okay, it's a little bit easier to use. Aesthetically, it's very, very clean, very slick. It looks very elegant. It looks like a bit of artwork, and you'd be more than happy to have it on display at the entrance of your house. While the PC, on the other hand, is very function-driven. Okay, it's a little bit harder to use. It can be a little bit clunky, a little bit ugly, you know, the cables and the boxes and stuff like that, and all black and whatnot. However, it's much more powerful. Okay, and so this one here, which one's a better product? Well, once again, they're both good products. Okay, but this one here, it really depends on the consumer. Okay, so who's buying it, and once again, the application. Okay, so both good products. Okay, this one here, the which one's a better product out of the 3? Well, all 3 were actually hugely popular. Okay, and all 3 were actually very successful products, but these one here, it really depends on timing. So the Sony Walkman, okay, was hugely popular back in the day when cassettes were, okay, that was the technology that was available at the time. Then CDs came about, and what they did is they modified from the cassette to the CD, okay, and so you had the Sony CD player, and then following that, you went to MP3s, and yeah, and the iPod was then produced. Okay, and so all of these are actually successful products, but it really depends on the time period and the technology that was available. So these products here are successful based on timing to market. Okay, if you were to come out with a CD player now as a product, it would be unsuccessful. Okay, you probably won't want to be carrying around something so bulky, okay, like that. Okay, once again, which is the better product out of the 2? So we got on top, the top left is the 787, the Boeing 787, and the bottom right is the Airbus A380. And then, so this one here, it really, like I was saying before at the start, okay, as a designer, you would have an objective here. Okay, an objective for a commercial aircraft is to really transport people from one location to another safely and reliably. Okay, and quite cheaply. Okay, and the two different manufacturers, Boeing and Airbus, chose to do this in different approaches. So the Airbus A380, what they did is they stuck with more known technology at the time. Okay, but what they did decide to do is take to really upscale it and to take more passengers from A to B. Okay, and which what it does is lowers the cost for transporting that person from A to B because it's shared with a lot of other people. Okay. The Boeing 787, what they did decide to do for this one is to use a similar size aircraft and transport similar number of people as previously. However, they aim to do this more efficiently. Okay, and so there's a lot more newer technology. There's new motors designed and developed for this. There's also lots of carbon fiber implemented on the aircraft and lots of other new manufacturing and new technologies put in there as well. Okay, so they're really solving, I guess, the main overall objective to get people from A to B, but one saying let's take more people there to improve efficiency, and then the other one saying let's take the same people, but let's improve the technology to do that. Okay, now both of them had hiccups, okay, along the way. The A380 had some wing creases during some testing of their wing structure, so it had a slight delay in the actual aircraft being certified. And then the 787 had troubles with, once again, certification and motor issues originally. Okay, but these have all been resolved now. Both aircraft are actually running and running successfully. So they're both viable and successful products, but they're just looking at different ways to solve the same problem. Okay, so when it comes through to products, okay, what makes a good product or bad product? It's not just design, but it also comes through to timing. So when you're actually bringing the product out to market, your market or consumer, what application are you looking at, any innovations or technology that it's applied. So there's many different factors that we'll see later through the lecture as well that are considered during the actual product design. Okay, so when it comes to the formality of the unit, okay, the lectures are 2 hours long. Okay, you'll see here I've got all the lectures listed 1 through to 12. Okay, you'll notice that I put catch-up week on week 12. Okay, the reason for this is because catch-up week should be a time to catch up. And I imagine that lots and lots of students have lots of assignments due. Or they'll be due in that last week. So try and help with that. I'll put catch-up week then, so you can actually have a break from my classes at least and have those couple of more hours or few more hours to work on your assignments instead. Okay, so the lectures that we've got is obviously lecture 1. We've got an introduction. Okay, and we'll go through a bit of the PDS, product design specification, you'll see shortly. We'll go through stress and strain and strength, Moore's circle and safety, moments and bending, buckling, springs. We'll have mid-semester break. Then we'll return with 2 parts of bearings, so bearing part 1 and bearings part 2. Then there'll be design of non-permanent joints. So this is things like threaded fasteners and also looking at power screws. Then we'll go through, look at permanent joints, things like welds and sizing welds for a certain structure, power transmissions, catch-up week, and then the last week will be a unit review and your project presentations. Okay, so the lectures will actually cover formulations and processes themselves. However, you really need to ensure that you've got the right approach and applicable application of those formulations for a particular problem. So you'll see that this particular lecture is a little bit more on the creative side. Okay, but as we progress through the unit, we'll be having a lot more calculations. And there's some methodologies which are quite important when actually applying these calculations. Now this unit does offer quite flexible learning. Okay, the lectures and tutorials will be recorded, as well as having the material uploaded as well online. So what's really required from the students in this particular unit? Well, students should be able to conceptualize solution to design problems and then apply mechanics and machine design principles to undergo detailed design of these conceptualized solutions. In other words, you're doing creative problem solving to solve a design problem, and then applying the calculations that you'd see from lectures 2 through to 11 to then size any of these conceptual designs. So taking them from a concept through to reality. Okay, and these are for static applications. In advanced mechanical design, we'll do that for dynamic applications. So is this learning material helpful? Okay, well, like I mentioned before, mechanical design, advanced mechanical design are really capstone units for the mechanical engineering course. Okay, a lot of the other units which you've done already sit underneath these units, and you'll notice that we'll be pulling information from all the other units or many other units into this one, sort of brings it all together. So you'll feel a bit of a sense of accomplishment and a bit of this is, starting to formulate, and you'll feel like you're ready to go out to work once you've finished these units. So this is really essential for design engineers in the workplace. Okay, and it'll help also from your general project management point of view as well. Okay, which is really useful for you finding a project and also when you're doing work at an industry, because essentially you're doing a series of projects. So does the unit improve your skills and extend your learning? The unit helps consolidate a lot of fundamental calculations you've learned previously, also dealing with complex load scenarios, and as well as conceptual design problem solving, okay, which is a real creative side of the unit. Okay, and also look at the treatment of material strengths in various situations for sizing particular components. So you'll complete the unit, be able to solve real life design problems in static situations, and then combine with advanced mechanical design, be able to solve dynamic problems, which will then help you directly for refining your project and make you industry ready. So absolutely, okay, this unit will improve your skills and certainly extend your learning. Okay, is the unit well organized? Okay, well, I've been teaching this unit nearly for a decade now, so it is quite polished. The material is all uploaded and available online. The unit plan is all up to date with the assessments, and I'll get through to those shortly and when to roughly expect them. The marks we provide in a timely manner. Okay, it's generally 2 weeks. Okay, and I guess what also helps with this unit being organized is, I guess, the UTI feedback that I get each year from students and feeding that back into the unit to try and improve it year after year. Does this unit challenge your thinking? Absolutely. Okay, like I said, this is very unlike many other units you've done before where you've done lots of calculations. This unit is all about creative problem solving, okay, and looking at how you apply your calculations to solving real life problems. Okay, and there's lots of ways to implement these equations, and you can make your life very difficult, you can make your life much easier. Okay, and you will see there'll be assumptions along the way and how you can be conservative as you're applying these assumptions. So it will certainly challenge your thinking. Okay, so I'll guide you through a very pragmatic approach to solving these problems, especially even some form of creativity if you've never done it before. Okay, and so we'll go through and design real life problems, and real life problems are generally very open-ended. Okay, so they're always going to be challenging, but yet very enjoyable and rewarding, where you actually get to see you transforming a concept, something you've got in your mind, through to reality and going through and building that as well. So will you be satisfied with the unit? Well, from the years, from what I've seen, past mechanical design, advanced mechanical design, both very popular and favorite units within mechanical engineering course, because students really get to see everything sort of coming together with these units. Okay, and these have a really nice balance between theory, the problems, it's challenging yet rewarding, and you also have that, the theoretical side as well as some creativity side as well. Okay, as engineers, we all like some creativity and coming up with our own solutions. Okay, so you will find this unit very satisfying and rewarding. Now the tutorials down there, it says they're 1 hour. Okay, I like to throw in a little bonus for students, and I generally run tutorials up to potentially 2 hours. So there is a 2-hour slot allocated. And so, yeah, some of these tutorials, depending on how many questions are and how students are absorbing the material, or if they've got any questions, we can run up to 2 hours there per week, which is a little bonus extra hour from me to you. Assessments. Okay, there's 4 assessments throughout the semester. Okay, so we have a minor project. So this is a conceptual based project which really follows from what material we cover in the first lecture, where you actually go through and design, or actually conceptually design a component or system, and these are done in groups of 2. Okay, then there's a theory based problem. This one here is a bearing calculation, so it will follow week 7 and 8. Okay, so week 7 and 8, you'll do your, I should say lecture 7 and 8. You'll be doing your bearings, part 1 and part 2. After bearings, part 2, you'll get the assignment, and you'll generally have about 2 weeks to do that. The minor assignment, this one here, you'll probably get around week 2, the latest early week 3. Once again, that will be in pairs. Your major assignment, this one here, will most likely be a design and build project with a report that details your detailed design calculation, etc. And then in the final lecture, you'll then present your design to everyone else. Now this year, I'm looking at implementing the Warman project, okay, for this one. So this Swarm project is a university competition, okay, which runs nationally, and so it's actually a small design and build project, okay. And so you'll see information posted up on the up online very soon about that, and I'll send out some announcement in regards to that. That particular assignment will be done in groups of 4 or 5 students, and once again, I'll send out an announcement depending on how many students we have in the class, how it all works out. Then the last assessment is the exam, okay, and so this is really the individual assessment component of the unit, where I get to see actually your understanding of the unit. Okay, and this one is mandatory to pass. Okay, it has very similar style questions to tutorials, and once again, the tutorials will have some past exam questions in there to show what they're like, but it actually has a range of different difficulties, from fairly easy like lecture examples, through to moderate like tutorial questions, through to difficult, which is like an assignment style question. Okay, so once again, please come along to the tutorials. Okay, the unit is very heavily applied based, so the tutorials are very heavily, very beneficial. So will the assessments in this particular unit evaluate your learning? Well, absolutely. I mean, the first assessment looks at the creative problem solving, or free thinking, okay, which is really the heart of this unit. The second assessment really looks at your application of component design calculations. The third assessment looks at all aspects. It looks at creative design, detailed design calculation. It also looks at your capability of working in teams, forms of manufacture, CAD capabilities, etc., and also presentation skills. And then the last assessment is really looking at your fundamental knowledge throughout the whole unit on an individual capability. Now, there's a few different textbooks here which I recommend. Okay, a lot of the unit will be referring to Shigley's, okay, which is this particular unit, this particular textbook up here, but other textbooks as well that I'll be referring to: Fundamentals of Machine Component Design, and also Notes on Design Analysis and Machine Elements. Okay, so getting into the unit itself. So I'm not sure how many people have actually designed before. and what you've actually designed. But generally, I have several students who've done some form of design before. Now, mechanical design, advanced mechanical design, there's somewhere around 150 to up to 200 students. So there's a very small percentage who have designed previously. Now, if you haven't designed, that's what this unit is all about. Okay, so we'll go through things like what is design, what are the different types of design are there, and what are the main activities in design. Okay, and we'll go through some of the basic principles to help you design if you've never designed before, and eventually, these techniques will become inherent in your design process. So there's different forms of design that you may have heard of. Okay, there's industrial design. Okay, so this has lots of visual renders, more fashion related. Okay, image detail, image details, etc. There's construction design and structural design, so these are more civil related. Then there's process design, which is probably a little bit more relating to like chemical engineering, and it actually applies to all engineering forms really. There's always lots of different processes which you're doing, even like manufacturing processes, for instance, that mechanical engineers will work with. But the main two that we're really working with in this unit is we're looking at mechanical design and product design. So mechanical design observes standards and also looks at standard components, bearings and seals, etc., and sizing these, and also looks at creative problem solving within that as well. Product design looks at all brand new designs, so there's no standards. Often you'd be even designing things like fasteners, etc. Okay, so that's what this unit is really looking at. So in life, okay, we have lots of problems, okay, and what we do is we solve these problems in order to survive. So in other words, we're essentially designing to survive, okay, and this started from a very early stage, such as like cavemen. Okay, they were probably some of the earliest designs, very simple, but they were needed to help survive. Okay, and things like they designed shelters, designed cutting tools like axes, designed clothing, the wheel to help transport, hunting tools, etc. So what is design? Well, design is the application of creativity to planning, the optimum solution of a given problem, and the communication of that plan to others. So if you have a look, there's some key words really in that. It's applied, there's creativity, there's planning, there's optimum solution, okay, not just solution, but optimum, and then there's communication as well. They're the main tasks that are really involved here. Okay, so design is problem solving where there is no unique correct solution like a mathematical problem. Okay, you put numbers in, you don't get a certain number out in this particular case. Okay, everyone has very different upbringing, lots of different experiences, etc. So based on these different experiences, you're going to have vastly different solutions to a particular problem. Okay, so a real life problem has many different solutions. So there is a lot of creativity involved to try and generate these solutions. You'll notice that this optimum solution is what we're trying to aim towards. Okay, so what we're saying here is that not any solution will do. We're always striving for an optimum solution. And when we're looking for an optimum solution, we're trying to maximize or minimize critical factors or variables. Okay, so as a result, we need to identify what these critical variables or factors are. Okay, and so we'll investigate this a little bit later in the lecture. We're looking at constraints and criteria. And then what we're doing is we're communicating this idea or solution of a problem to others, okay? And so we can present ideas, concept, detailed designs, manufacturing drawings, etc. through to different people. Okay, and so that's something that you'll be doing definitely for your minor assignments. You're generating a solution to a problem, and then you're communicating that to others, and essentially be communicating to your partner in your group, but as well as you'll be communicating it to me. Okay, now more specifically, engineering design is the process of devising a system, component, or process to meet desired needs. It's a decision-making process, often iterative. It's, as far as I've seen, it's always iterative. in which the scientific principles, mathematics, and engineering tools are applied to convert resources optimally to meet a stated objectives. Okay, so you really need to know what's my objective in order to generate a solution. Okay, and that's why some students will struggle trying to generate solutions to a problem. And that's because they probably don't understand clearly what are you trying to solve. And so there's techniques where you can actually try and make it a lot clearer, and I'll show you that a little bit later in the lecture. Okay, now when you're designing, okay, it's a little bit like this. You'll start here, okay, and you'll feel like you're getting nowhere. Okay, you'll be generating some solutions, you'll be sort of heading in this way, and then you'll find out there's problems with those solutions, so you'll be heading backwards, and so you're actually not really progressing. Okay, however, over time though, you'll find that from bad solutions, you're generating some ways to solve that, which will kick off other possible solutions, and you'll eventually sort of converge towards a solution. Okay, now if you're aiming towards an optimum solution, this will just keep on going and going. Okay, and it just keeps getting more and more refined. Okay, but you'll notice that there's no real squiggles in the vertical direction because you're converging towards a solution. You've got a solution which works, but you're just making it better and better. Okay, so it can feel sometimes like you're bashing your head against the wall a bit when you're designing, but trust me, it is part of the process where you're actually taking some steps backwards as well as taking some forwards. So a key starting point in design is actually understanding the problem, okay, in great detail. And so what is the problem? Well, there's generally two types of problems. There's a well-defined problem, and then there's an ill-defined problem. Okay, now well-defined problem, as it states, is a problem which has, it is well-defined. You know exactly what you're trying to solve. Okay, and so, for example, you may have a gearbox, okay, or your client has a gearbox, and it says they could approach you and say, in this gearbox, this particular bearing here, number 3 or whatever, keeps failing. Can you find, what's wrong with it? Okay, and it's quite easy. You can have a look at what loads are going in, what loads are going out. You can find out, what size of gearing is, etc., to calculate some loads, and you can actually then calculate what the expected life is, and you can then resize it. Okay, very easy to do. It's like it was into an equation. What's difficult for engineers, though, when it comes to designing, is ill-defined problems. Okay, and these are problems which are very vague and very open-ended. Okay, and they're very difficult to solve. So, for instance, a client could come up to you and say, too many people in car accidents, fix it. Okay, and there's lots and lots of different factors which could be contributing here. It could be, bad training for drivers. It could be the cars aren't safe enough, or the roads aren't well enough. Or good enough. There's not sufficient training or signage, etc. Okay, and so what we do with an ill-defined problem, okay, is these are really difficult to solve, okay, and requires a lot of analytical thinking. So what we need is to further define the problem. And what we generally do with an ill-defined problem is find out what's the main objective we're trying to solve, and then try and convert this particular problem into a series of well-defined problems. You break it down into smaller ones. So for that vehicle one, you might say, well, I'm a civil engineer and I know roads really well. And so you can then apply your knowledge of roads to have a look at the roads in high detail and say, well, what, these look safe enough. Okay, so it's not that. Okay, so you can eliminate that and then look somewhere else. Okay, or you can say, well, no, the roads do have an issue, and you can then solve that. So when it comes to ill-defined problems, okay, we try and make these into well-defined problems instead. And so when we start generating solutions, we must also ask ourselves, will the market accept it? Will it be cost effective? Okay, will it be ready at the right time? Will it be good enough, etc. Okay, and these are different questions that you can ask yourself which help you to measure a solution's success. So what different types of design are there? Okay, well, there's 3 main types. So there's original design, adaptive design, and variant design. Okay, Original design, these are development of a new system to perform a new task or one that hasn't been solved by other means previously. It's essentially designing something from scratch, something that didn't exist previously. Okay, so original designs, these are new designs, very innovative, need lots of research work, knowledge, and creativity. High maths creativity are essential. Okay, and these are generally called creative designs. An example of an original design will maybe like the first clock ever to exist. Okay. Adaptive designs, so these are using known and established solution principles to meet new requirements. Okay, these are a slight modification of an existing design. So generally there's a lot of cross-pollination of designs or technology when it comes to adaptive design. So it's taking one thing and applying it to another. And so adaptive design example of that would be converting that mechanical clock that you had before into a wristwatch. So it's existing technology of that timepiece or timekeeping piece, but then what you're doing is you're adapting it to a smaller scale, so it's such that it fits on your wrist as a watch, and so then it becomes a whole new product on its own. Variant design, okay, sizes and arrangements of aspects of a given system are altered. However, the solution principle and its application remain the same. Okay, so it's essentially modifying an existing design into a new idea by adopting new materials, methodologies, manufacturing, etc. So variant designs, so these are basic modifications to an existing design. It would be saying, well, you've got that wristwatch, I want to change the face type, or I want to change the color or the shape slightly. So there's lots and lots of variant designs that occur, okay, because they're not very costly. These are very simple design changes. Now, when it comes to products, there's really two types of products. There's static products and dynamic products. Static products, okay, these ones, the concept remains virtually constant over long periods of time. Okay, product improvements are through incremental design of the subsystem and on a component level. Okay, static products are characterized by little concept level innovation, okay, on the subsystem or component level or manufacturing. These are where you might see some innovation, but from a concept level, there's very little innovation. These are very well-defined designs, okay, because they're very well understood. They've remained stagnant over long periods of time. They're a well-defined problem. They comply with a broad range of standards and codes of practice, which helps them become well-defined. There's high existing knowledge of the customer requirements, okay, so it's easier to design to satisfy your customer. There's high predictability in the project planning, costing, and implementation because there's a lot of experience working with these products, and they're relatively low cost. Okay, so relatively low risk, I should say, because they got high predictability. So you can see here on the left, we've got the train. Okay, the high concept has remained the same for a very, very long time. Okay, other forms of static products would be things like a car or a bike, and I generally have some pretty good examples in the lecture from students. Dynamic products, okay, these ones are from a concept, very new, and changes at an overall system level. These are characterized by major concept level innovation, high creativity and innovation, limited standards and codes of practice to work from. There's high risk associated with these products. However, there's significant benefits if they're successful. They're relatively low knowledge of the market, and so there's a huge emphasis on market research. And there's low level of predictability in the project planning, costing, and implementation. So these can become very risky projects. So here it says a Virgin Galactica spacecraft, which is for commercial space flights. Okay, very, very risky. I think they did have some failures as well, but if it's successful, it will be hugely popular. Other examples of dynamic products would be things like the hovercraft, and that first came about. So a vehicle that's possible to operate on land and water. Concorde, supersonic flight, SpaceX as well, reusable rockets, etc. But in reality, most products actually fall somewhere between a static and dynamic product.
Okay, and things like the electric car that's coming out, or becoming quite popular now with Tesla, for instance. Um, these are somewhat of a hybrid between static and dynamic products. The car itself is a static product, but the electric powertrain is a dynamic product. It hasn't really been done on that scale successfully before. Now, can you learn to design? Okay, a classic example of this is Kingdom Brunel, as you can see here on the left. Okay, he's an English mechanical civil engineer who designed railways, bridges, dockyards, ships, etc. He designed the first major British railway, the Great Western Railway. He designed steamships, including the first propeller-driven transatlantic steamship. His father taught him drawing and observational techniques from 4 years old. Okay, so he started quite young. Okay, and he was encouraged to draw interesting buildings and identify any faults. So you know, he was sort of forced or trained to try and generate creative or creative solutions to challenging problems. Okay, and then to challenge his thinking and look at what's the faults with these? How can I try and reverse these negatives and improve these designs to make them feasible? He learnt Euclidean geometry, French, and basic engineering principles by 8 years old. Now, although his designs were not always successful, they were often contained innovative solutions to very challenging problems. Okay, the River Avon, it had the longest span of any bridge in the world at the time of construction, spanning about 210 meters out of a height of about 61 meters. In 1852, he designed his third ship, okay, the Great Eastern, which was intended for voyages to India and Australia. It was about 200 meters long, capable of carrying about 4,000 people. So it was a huge ship. And it was actually designed to cruise non-stop from London through to Sydney and back, because engineers weren't sure if Australia had any coal reserves or not. So they had to make sure it could hold enough fuel to get here and back. And so it remained the largest ship that was built until the turn of the century, which is very, very impressive. So how did he actually become, such a great designer? Okay, it's really through lifelong learning and practice. Okay, he started young. Okay, and so you start to build this library of design experience in your mind. And I'll go through and make some analogies, about this, and that, when I was talking about Lego before, what you do is you've got all these set Lego building blocks, which you're actually referring to when you're building something out of Lego. And the number of pieces that you got are quite limited, okay? But you can keep these in your mind, okay, and think, well, if I'm building something, I need this piece to go in here to finish the design off, or to complete this aspect of the design. And so it becomes a little bit easier, okay? And I guess that's why it's for children and whatnot, okay? But when you're designing as an adult, you've essentially got infinite creativity and lots of different components that you can pull together to solve a particular problem. And one way of getting this library of components together in your head is actually just through design. Okay, there's no better way to know, well, I can use this component off the shelf, or I can have this particular concept to, have this mechanism to solve this particular problem, unless you're actually getting through the practice of designing. So it's all about lifelong learning and practice, getting your hands dirty and actually doing the work. So yes, you can absolutely learn to design. Okay, it's just about starting and just continually practicing. So what are the main activities in design? Well, first of all, you need to gather and present the facts about a problem, product, and or process. You need to clarify and analyze relationships between the problem, products, and processes. You need a way of measuring the performance of your idea or design. You need to highlight strengths and weaknesses and compare alternatives to try and improve them. You need to diagnose why an area is weak or strong. Okay, so you can actually reverse the negatives and improve your design. You need to provide redesign advice on how a design can be improved. Okay, all of us, when we're designing, we all don't like others to look over our designs and be critical. However, we all have lots of different experience, Okay, and so what happens is, you know, someone on your shoulder may offer some really good redesign advice. Okay, and so it does become quite difficult, but it is really beneficial to your design to have others look over it and allow that redesign process to occur. Okay, it will improve your design a lot. Predicting what if effects. Okay, this is Murphy's Law. Okay, what can go wrong will go wrong and at the worst possible time. Okay, so you need to think with your design, if someone's using this, what can actually happen. Okay, if someone, does something with the particular design. For instance, I use my water bottle, my Voss water bottle a lot as a prop in my lectures. Okay, and I'm pretty sure the designer in Norway who was designing the water bottle wasn't thinking that a lecturer in mechanical design in Australia would be leaning or twisting or trying to bend the water bottle, in a lecture as a prop. I guarantee they weren't thinking of that. Okay, but when they're designing, they're thinking, well, what if someone drops it, or what if someone, leans on it or something like that. Okay, and so then that actually is long enough, and so it can survive, and so then it can allow for these other different effects to occur, and your product still survive. You need to be able to get improvements. Okay, knowing where your problems lie in your design, but then allowing those improvements to occur. And then the other one is to allow iterations to take place. Okay, we don't like to continually working on the same problem, but iterations do refine your designs a lot. And like I said, even my lecture notes here, they've been refined numerous times over. Okay, just through different iterations. So as a designer, we must foresee any interactions of our planned object or design during operation. How do you think the operator will use it? Okay, designer must implement Murphy's Law, okay, through the what if effects. And most of all, design is not merely calculations. Okay, we cover detailed design later, okay, from weeks 2 onwards. However, design really starts from the conceptual phase, which is what we're doing in this particular lecture. So, design is really a decision-making process. Okay, now without any design experience, there's a high probability of working towards a close to optimum solution if you apply this design process flowchart. Okay, now as an experienced designer, these steps do occur still. Okay, we still apply this, however, it's a little bit more inherent. Okay, now if you've never designed before, you would most likely use this chart as a way of iterating or working through solving problems. So design is a decision-making process, and engineers used to like physical realization of machines, devices, and systems. And so this flowchart can help new designers work towards an optimal solution. And so what we do is we start off first of all with our task or problem. Okay, so there'll be some form of issue somewhere, in industry, for instance. And your client will then go through and contact you, okay, and say, well, I've got this particular problem, okay, are you able to solve it? And if it, lies in your capabilities and it's something that you're interested in, you can then proceed, and what you'll do is you'll then gather some information, okay, and so you'll be speaking to your client, collecting more information about that. And this sort of even applies for your assignment, which you'll get, like your major assignment. Okay, there will be a problem, okay, which starts here. There'll be a confrontation. I'll give you the assignment sheet. And then you may say, well, I've got this particular way of solving it, but I'm not quite sure if it works. So you will then gather some more information from me, okay, your client, to work out if it will work. And then from this information, you'll start to define the problem very clearly. And then once you've got a very clearly defined problem, you can then start to create some solutions. When you start to create some solutions, you'll then have to evaluate these solutions so that you can make a decision and choose one of them. And this one decision will then become your final solution to the problem and make your client happy. Now, one thing you'll notice is that there's lots of arrows here going backwards and forwards. Okay, because what you can find is that you could get to the problem definition and creation phase, and you find that your problem could be overdefined. Okay, and you can't actually create any solutions. So then what you'll do is you'll go back to the information, you'll redefine your problem, and then it could be too vague, so you have to go back, etc. Okay, or you may even come to the evaluation phase and you're finding it difficult to evaluate your solutions to then have one. You might find that 3 or 4 actually work, and so you could go back to your problem definition, for instance, and you could define the problem a bit more, which will then help narrow down which concept you work. Okay, so this is, I guess, a really fundamental flow chart for helping you work through design. We'll go through each one of these little steps in a little bit more detail. So what type of decisions are there? Well, there's 3 main decisions. There's fundamental, intermediate, and minor decisions. So fundamental decisions, there's fewer in number, but these have huge importance. Okay, they really dictate if the design is going to be good or bad. Okay, fundamental decisions are made at the start of a design process and often unchangeable without substantial redesign. Okay, and we'll see the effects of that later. Intermediate designs, these are an extension of and supplement fundamental decisions. Okay, any intermediate decisions may spring from one fundamental or another intermediate decision. Okay, these decisions may be changed, often without difficulty and expense. And then minor decisions, these occur vast in numbers and most often concerned with design details. And these usually change with minimal difficulty or expense, and lots of them occur. Okay, and so if we were to sort of plot this on a particular chart, you would have here the cost of change versus your design progress. Now, if you haven't progressed very far and you start to make some changes, it's not going to cost you very much at all. But if you've gone well and truly into your design and you're somewhere here, you can see that it's going to be huge cost to then make those changes. So this is all really about 90% planning, 10% doing. If you're doing conceptual design work, you want to get your concept right from the start, and you want to make a lot of those big decisions with your conceptual design in this phase down here. You don't want to be making conceptual design changes over here because it's going to cost you a lot. Now, in this particular unit, if you're, let's say, doing your major assignment, the cost of making a late change in your major assignment will be having to redesign it all. You could have a late submission, you could get a bad mark, okay? Or your product or your solution might not be fully finalized. It might not be finished because, you know, you've got to the deadline, okay, and you've had to redesign so late. In industry though, if you're making decisions really late, you know, projects can run overtime. There'll be huge financial penalties for this, okay? And I'm sure your line manager will be frowning upon you for these late decisions. So it's really 90% planning, 10% doing. Spend a lot of time here in your conceptual phase, okay, making a lot of the decisions, okay? So although we only spend one lecture on the conceptual design, I think it's got much more importance than the detailed design that we do for the rest of the unit. Okay, so there's a huge emphasis, okay, on that. And now I showed those that flow chart before, okay, for the decision-making process for the conceptual design phase. That sort of sits in here, okay, so that's where that other flow chart sort of sits in. However, if you look at a full product, we actually have the same type of flow chart where you have here from the market. So what product or what void do we have in the market? Then we can go through and specify the problem in a lot more detail, which is more gathering our information. We can then do our conceptual design. We then, once we've got our conceptual design done and we've decided on a project, we can then go through and do the detailed design. Detailed design is all about doing, you know, the numbers and equations. And if you've got a beam, how big should the beam be such that it can withstand loads? What material will it be made from? So conceptual design, you can say, it's more like sketches and whatnot, and what the solution looks like without any, you know, details of, you know, dimensions, etc. Detailed design, this is looking at putting numbers and, you know, dimensions to certain aspects of your design, specifying a lot more detail. And then following that, once you've done your detailed design, you'll go through into manufacture, and then following that, you can then go through to back to your marketing again to actually sell it. Okay, and so there's lots of these little charts which exist. Now, part of design is communication. Okay, and so you'll notice that there's written, oral, and graphical forms of communication. Because what you need to do is really sell your idea and sell yourself as a designer. Okay, and so your presentation skills are very important. Okay, to try and show that you have evidence of the problem definition. So you need to show that you understand the problem well. You need to show evidence of invention and innovation with your solution. You need to show evidence of foresight. Okay, looking at how your product will actually be implemented in reality. And you need to show evidence of logical argument, okay, logical ways of solving these problems. And so there's lots of these charts that exist. Okay, here's another one. Once again, going from your task and some marketing all the way through to your final solution, your product documentation, etc. But working through that whole process. So as a designer, it's your responsibility to seek out necessary information from customers. Okay, so you need to find out, what's their viewpoints, what specifications do they actually want, what's their reactions to some solutions that you generated, and also what's some safety aspects that are required as well. And so here you can see different types of information that you may gather while working in that information phase of your chart here. So when you're looking at this information gathering point here, you'll go through and maybe gather some bits of information like this. Okay, what helps with analyzing some of this information? Well, you can look at parametric analysis, so cross-plot parameters to find relationships, both logical and illogical. A needs analysis, so analysis of reports, interviews, questionnaires, or you can have a matrix analysis. So matrix, which is competitors on one axis, model types on another, for instance. Okay, so there's lots of other ways to analyze this information as you gather it. So when you collate this information though, we need to define our problem very well. Okay, and so when collating information of a problem, what we generally do is create a product design specification. Okay, and this helps identify the key requirements of the design. So the specification itself, okay, is dynamic rather than static, so it's always changing. And the reasons for this is that your client may have, they might not like some of the solutions that you're generating, or they may have some other requirements that are required, okay, for their particular problem. And so as more information gets gathered, this goes into your PDS, and so it gets updated continuously. Okay, for instance, an example of this will be your major assignment. I'll give you an assignment sheet. One group may come up to me and ask me a question about their about the problem. I might give them some information, but then what I will do is I'll give that information out to everyone through an announcement online, and so you'll be gathering some more information. So then from that, you may update your PDS for your problem. So the PDS document, okay, is a controlled document, not in SI style, so it's generally quite succinct and clear, so it's most often dot points, and it should attempt to quantify parameters in each area. It should be dated and numbered clearly, and all amendments noted are needed to be documented as well. Okay, so some things, which the PDS may look at are things like performance. Okay, what performance is required, the cost, sizing, competitors, shipping, etc. One on here which is on every single PDS is this one. Every single design that you do must be safe. Okay, so the safety will always be in your PDS, and you need to look at ways in which your design will be safe. Okay, so your PDS document will help you to generate solutions, okay, to the problems, and it will help define your problem so you can generate solutions quite easily. So conceptual design, okay, this occurs after your PDS has been generated, okay, and once the necessary information has been gathered, okay, you can then start to generate these ideas. And now there's two main goals of your conceptual design phase. There's a generation of solutions, and then there's the evaluation of these solutions. Okay, so when you're generating ideas, one thing to think about is that you shouldn't criticize, okay, or be overcritical. Because what happens is if you're overcritical, you can actually cripple some creativity, because even from bad ideas, you can actually then, or I shouldn't say bad ideas, but from ideas which may seem impractical, you can actually trigger some other really good ideas. By trying to make an impractical idea practical and solve it, you can actually have some really unique ideas. Okay, now practical solution is one which satisfies all our problem constraints. Okay, and you should only trash ideas that fail to meet our constraints and not our criteria. And I'll get through what constraints and criteria are shortly. Now, some methods to help creativity in a controlled convergence. Now, what I talk about controlled convergence is that flowchart I showed you before. That's a very structured approach to converging towards a solution. So there's some ways here that we can actually help our creativity. That's analogy, okay, finding similar solutions, applying ideas across disciplines, brainstorming, okay, working in groups and diversity and having lots of varying experiences applied to a particular problem will give very different solutions. Attribute listing, so this is breaking down the idea into much smaller parts, so even smaller well-defined problems, and looking at alternatives or solving those problems individually, then bringing it together. Checklist, this is listing the constraints and criteria of a problem, which is one thing I'll show you shortly. And then one in which I like here is inversion, okay, and this is inverting the initial concept, or instead of trying to solve the problem, you think about how you can eliminate the problem from the beginning. And there's a classic example for this one, which was back in the space race to the moon. NASA was looking at, obviously, or NASA and Russia were both in sending up, people into space in orbit where there's no gravity, and the standard traditional ink pen, didn't work too well. Okay, and so when they're trying to write, it wasn't successful. So NASA was then trying to solving this and coming up with unique pen ideas to try and have the ink to work. And then Russia's like, it's pretty cool. We just use a pencil. Okay, so that's a classic example of trying to reverse the problem, thinking about, well, what's the objective of the pen itself? It's just to get something down on paper. How can you actually solve this? There's lots of different ways. Okay, and you try and eliminate the problem to start with. Okay, now constraints and criteria, I find these invaluable in guiding decision-making or design decision-making processes. Okay, so if we look at constraints, these are a limitation or restriction with prescribed bounds imposed on an entity, project or system for achieving its potential with reference to a goal. Now, that's a dictionary definition, but if we're to look at it applied design, it's really a bound or limit in which every design candidate, so all your different concepts, must comply to be a valid or viable solution. So in other words, a constraint is a satisfaction of a constraint by candidate is binary. Okay, does it or does it not comply with what's required? Okay, and so this really limits our designers' freedom, okay, and provides very strict design bounds. It makes our problem very well defined. For a pen, for instance, a constraint is it must write. If you've got a pen concept and it doesn't write, okay, it's not a successful product. Okay, so you can trash that idea straight away. Criteria, on the other hand, is a standard rule or test in which a judgment or decision can be based. From a design point of view, it's a means by which the suitability of design candidates, so your different concepts, may be judged against one another. So criteria is, some candidates may satisfy criteria well, some may satisfy criteria poorly. So constraints are very black and white. Does it solve the problem? Does it not? Criteria is how well does it solve this particular problem. Okay, so our criteria is a grey area, and it's what we use to determine how well our product or how well our concept is. So I do normally have a bit of an activity which I get students to do for this one, okay, where I get students to draw a single line fits within a box traced around the outline of their phone that stands out. Now, from that basic little problem, the constraint is here. You have to draw a single line. Okay, so if you draw 2 lines, 3 lines, they're not valid solutions. The constraint is a single line. The second constraint is that line must fit within the envelope or the perimeter of your phone. So that limits how big this single line should really be. And then, so if this line goes outside of the bounds of your phone, sort of size box, then it is not a valid solution. So these are making it very binary. And then the criteria is how well does it stand out, okay? Because the criteria or the subjective part here is stand out, okay? And so things that you could do for this, you know, are using colors, etc., where you can actually try and make it stand out a lot more. Okay, now a lot of times students will think, oh, it's a line, it's got to be straight. A line doesn't need to be straight. You could have a zigzag line which covers the whole perimeter of your phone essentially. Okay, so you could have one big block. Okay, so that's a really simple example, some constraints and criteria of a problem. So, so what we want to do is evaluate our different concepts now. Okay, so evaluation is really to prove our design concept success. Okay, and what we want to do here is to avoid any gut feeling decisions. So we need to continually give opportunities for new concepts to emerge after reducing the concept numbers. We need to look for ways of reversing negatives of a concept, and skipping this step can be a false economy of time. You think, oh, okay, I've got a solution, that's it, all good, I'm going to move on. But the thing is, if you realize a little bit later when you're going through the detailed design calculations, you know, your concept isn't as good as what it should be, well, then going back to update that can actually be very costly. Okay, so when we're evaluating ideas, an optimum solution is one that best satisfies all criteria. So criteria, those gray areas that we're talking about before, an optimum solution is one that satisfies all our criteria and does it well. Okay, reversing negatives. Okay, this can eliminate or remove all potential good concepts. False economy of time. Okay, you know, designers believe progressing well ahead of schedule, but you could actually have a poor concept which later needs to be revised, and then you're behind schedule. So please invest time into your conceptual design. Now, in order to evaluate, okay, we really need a list of criteria. Okay, and then once we've got this criteria, we need an ability to estimate the importance of each criteria, the degree in which the criteria is met, and overall satisfaction. Okay, and so we have a matrix to try and help us do this. Okay, and what we call an evaluation matrix, which gives us structure and control to, you know, come up with our best candidate. However, it should be used with some caution because there is some subjectivity to it. So here's an example of an evaluation table. Okay, so you'll notice on the side here, we have our different concepts. Okay, now in this particular problem, what we're doing is looking at race car wheels. This is for a motorsport team. And so one concept is to get wheels from the US straight off the shelf. Another one is the wheel rims off the shelf with our own wheel centers. Another one is all our wheels are done in-house out of aluminium. And then another option is to have carbon fiber wheels all done ourselves. Now, these are our different concepts listed down. What we do is then list across the side here our different criteria. And these are cost, weight, development time, and performance. They're the main things that we're really looking at. Now, these will vary too, okay? These are just applicable for what we have, okay? But depending on what you're trying to solve, you may have lots of different criteria. The number beneath that, this is the maximum score a concept can get for each one of those. And so you'll notice that they're all 10 except for development time. This actually has 20. Okay, And that's because there's a higher emphasis on development time. So this is the subjectivity and the caution comes into it, because you can have different weightings. So for instance, for the motorsport team, we only have a 1 year life cycle for these cars, or development cycle, I should say. So from start to finish, there's only 1 year. And so we don't have much time to actually come up with a concept and see it through. So that's why development time is more important. However, if you're working for Formula One, for instance, okay, they may be working on a little bit longer time schedule. Okay, they may start the project earlier, but what's really important for them is performance. Okay, so they may bump this number up and drop this one back down. Okay, and so that's one thing that they may do. And then what you go do after that is you go fill in the numbers on how they score out of the best possible score for each concept. Wheels from the US, obviously cost these are going to be cheap, so they get a perfect 10 out of 10. Also development time, there is no development time. You just make a phone call, give your credit card details, they get shipped over, done. So you'll see it gets 20 out of 20 for that. Weight, it scores very poorly, okay, because they're quite heavy, and performance, because they're heavy, they don't score that great. Now, if you look at carbon fiber wheels, for weight, they get a perfect 10, okay, because they're light, and for performance, they get 10. However, for development time, they only score 5. It will take a long time for us to develop these. And cost are very expensive as well. So you actually see that the carbon fiber wheels, you think race car, oh yeah, carbon fiber, it's got to be good. Well, actually for us, our application, these actually are the worst solution. And what's actually best is a hybrid between rims off the shelf and our own wheel centers, which is what you see here. And this one scores 38 out of a possible 50. Okay, but close to that is actually wheels off the shelf itself. So that's sort of how we can actually come up with, using evaluation, to come up with a selection of a particular concept once you've listed quite a few. Now note that your evaluation criteria and the weightings may change over time. So your client, you'll be constantly in contact with them and you'll be finding out, well, is this still what you're after? Is there any more information? And you may add criteria, you may take some away, or you may even change the weighting depending on their requirements. Other design considerations, okay, which you may think about from a criteria point of view, could be things like strength, reliability, corrosion, safety aspects, stiffness, you name it. Okay, there's lots of different criteria which you could look at. Ways of assessing if a product or as a design concept is better than another. Okay, and it's really your responsibility to seek out the customer, client's viewpoints and selecting the possible criteria from that. Okay, now excellent detailed design. So this is all your calculations that we'll go through later. They can't rescue a bad concept. Okay, so even if you've done really, really good calculations, if your concept is rubbish, your overall design unfortunately isn't going to be great. Okay, so that's why I say there's a large emphasis on the conceptual design process. Okay, and it's just as important, or if not, I think it's more important than the detailed design phase. Okay, a lot of people can put numbers into equations, but how you do that creativity and problem solving, that's quite unique. Okay, so in practice, conceptual design, if done well, you can actually reduce the total number of parts. Okay, you can reduce complexity, you can reduce material usage and weight, you can reduce costs, you can reduce assembly time, reduce the number of drawings, reduce the number of parts, or types of parts, I should say, so you can have more standardization, common parts. You can have improved appearance, improved reliability, improved use of your facilities available, the list goes on. Okay, now if you've got a reduced number of parts, you actually don't have to do as much detailed design calculations. There's fewer parts to do it on, so you can be more thorough and do a better job of that. And so it's self-perpetuating. Okay, so although it's difficult to do conceptual design, okay, and it seems like it's something on the side, and don't seem productive because you're not putting numbers into equations and stuff like that. I find it's a lot more important because you've got all these potential benefits just sitting there hidden in the background, which can help your solution be very, very successful. So unfortunately, conceptual design is not a cookie cutter approach like detailed design calculation. It requires lots of lateral thinking and problem solving. Okay, and so that's why it just really happens through practice. Okay, design for manufacture. Okay, so with the generation of ideas and settling on a concept, it's important to think about design for manufacture. Okay, you may generate further design iterations in order to improve your design for manufacture. So although you've got a solution, you may tweak that solution, do some more iterations to improve its manufacturability. Okay, a bad example of an example of bad design for manufacture was the DeLorean that we saw at the start. Okay, they were trying to apply lots of different and new and unique manufacturing techniques, which ultimately made the product unsuccessful. Okay, so design for manufacture can have lots of benefits, as you can see here. And then there's lots of sayings out there about design. So perhaps a major single contributor to the operating reliability is simplicity. Okay, and the superior design is one which encompasses the necessary operating and protective functions with absolutely minimum number of components and connections. Okay, and the only way you're going to do that is really through good conceptual design. And you don't have to come up with the best conceptual design straight away. What you can do is have a solution. It may have lots of parts to do it, but then you think to yourself, well, let me do further iterations of that. Can I amalgamate some parts? Can I improve functionality or performance by taking some parts out or modifying them, etc. Okay, it's all about iterative approach. Okay, if you can simplify something, you will automatically increase its reliability and cut costs. Okay, and also simplifying something means you can produce it a lot faster, less calculations, etc. For your major assignment, it becomes very, very handy. And like I said, we'll be doing the Woman project for a major assignment. And trust me, these Woman projects can get very, very complicated and tedious. So having a very simple solution, spending a lot of time in the conceptual phase, can save you in the long run. Okay, keep the design simple in order to have good reliability. Okay, and there's lots of other sayings as you can see here, and one which I like is, good design and creativity. The greatest gains are obtained by those willing to risk defeat, and so trying to push the boundaries and looking at really creative and unique solutions where they could potentially fail do have on the horizon really successful gain to be made. And so engineering design, is it a science or is it an art? Okay, and here you can see some different forms of design solutions which do look very artistic and quite beautiful. Okay, and this is saying here, art without engineering is dreaming, and engineering without art is just calculating. Okay, and some other examples, some really nice design solutions which look very elegant. Okay, and you'll see that form follows function, and we'll touch on that in I think it's week 3 lecture. Okay, and you'll see that when your designs actually look right, generally they are right, and there's a reason for that. Okay, well that concludes lecture 1. Okay, and I'll see you in lecture number 2, where we start looking at stress, strength, and safety. Thank you very much.